Okay? And finally, I'm going to be talking about inverse optimization. Okay? So what I'm going to do is switch gears, right? And try to think about how to model your optimization problem in the first place when still there are some parameters that are not known. Okay? But the way that I'm going to do is I'm going to use data, right? And specifically the methodology I'm going to be talking about is called inverse optimization. I'd like you to think like, what is this inverse? What does that mean, right? It's an optimization, but it's inverse optimization. So I'd like you to think about this problem. So recently Amazon announced this kind of competition where they ask researchers to, so they basically give researchers data, and data are the route decisions made by drivers. So what Amazon does as a central planner is they assign tasks to drivers. And tasks, they could be like set of packages to deliver. And they give packages to you, and you deliver to these customers, you deliver to these customers. And what they do is they observe how they choose route decisions, right? And what they've realized is that, well, when they assign this task to different drivers, they had some expectation. And their goal is to minimize something or optimize something. Let's say minimize the total delivery time or minimize the number of like customers that are missed or something like this. But it's almost always that drivers behave in a very unexpected manner, right? In terms of route decisions. Okay? So they give data to you and they ask you to, hey, is there any way to actually reverse engineer or infer their decision preferences based off of the actual routes they actually chose? Okay? So for example, what is the left is the decision that's predicted by Amazon by solving their own optimization problem, whereas what you see on the right is the driver's decision. And whatever is highlighted in boxes, they see some kind of, they show some differences between these two routes. Okay? So their goal is to understand the way drivers make decisions so that they use that knowledge, right, in their optimization so that what they predict is actually very close to the actual behavior of the drivers. Okay? And this is, if you think about it, an inverse problem in the sense that you try to learn some parameters of decision makers from their past decisions. Hence, inverse. Okay? So I'd like you to think about in general, right, some system that generates decisions. Okay? But you actually do not know how that system is generating decisions. For example, you don't know the coefficients of the objective function that the system is using, but all you can observe is the decisions that it generates. Okay? And the problem is, well, given those decisions, can we actually infer the parameters of an objective function of that system? And the system could be like human decision maker, could be some recommender system, whatever that is that uses some kind of optimization. Okay? And why that matters is because once you quantify the decision maker's preferences and express them in terms of some kind of objective function, that you can make a good prediction as to what's going to happen in the future, or you can even find a better optimization model that is representative of the decision maker's behavior, or in an cooperative setting, you can also make decisions for them. But in an adversarial setting, you can also try to, right, interdict or kind of interfere their decisions as much as possible if you know how they will behave. Okay? Okay, so that is called inverse optimization problem. So the goal is to infer models from decisions. And when I say infer the models, I'm saying infer the parameters of the model. Okay? So the objective function is unknown, not uncertain. Decisions are observable. These are the two premises for this problem. Okay? And let's focus on the objective function parameters, right? Try to find the objective function parameters for the underlying optimization problem so that your observed decisions or the observed decisions from the decision makers are actually made as optimal as possible. Right? By finding objective function that makes the observed solutions as optimal as possible, you're kind of explaining their optimization behavior. right? It's a relatively new, very popular technique. Still, there are a lot of opportunities, I think. And now that goes back to this story, right? Danzig's challenge in how to formulate his own personalized diet problem. So what if I ask you to, hey, can you give me your past 2 weeks diet behavior in like vectors in some way? Then what I can do is I can formulate a diet problem that can actually replicate your 2 weeks diet behavior. And that way I can make a prediction as to what you're gonna eat, a type of meals that you're gonna take, right? Inverse optimization. And it's actually inverse optimization, how it's been used for real problems. Diet problem was one of the application areas. Okay? And it's been used for transportation where you try to, well, infer the arcs of the network, which is pretty much like the Amazon's problem. The second application here is quantifying risk coefficients in portfolio optimization. So instead of just formulating or deriving the covariates of like between different assets, why don't we actually look at the actual transaction data from your customers and try to infer their actual perception of risk? Right? That's one thing. In the electricity market, some efforts have been made to elicit, so infer some preferences of consumers by kind of observing the way they consume electricity, of course. Um, you might have actually heard of inverse reinforcement learning. What is it? IRL. When you formulate a reinforcement learning model, you have to define the reward function. But often it's the reward function that is trickiest to determine. And depending on what your reward function is, your policy is going to be very different. So instead, can we actually look at some past trajectories of agents or experts and try to reverse engineer the reward function? Okay, it's been that work. And one application that I've been using inverse optimization for is the radiation therapy treatment planning problem, where doctors spend a lot of time in well, playing with a lot of different parameters to find an optimal treatment plan. Okay? And they give me some treatment plans that they think are good, some plans that are bad. And what I can do is use inverse optimization problem to infer all these parameters that the doctors are supposed to enter in this software so that the resulting solutions will be consistent with what is perceived to be good and as far as possible from what is told to be bad decisions. Okay, one way to kind of making sense of inverse optimization. Okay, so how do we formulate it, the inverse optimization? To talk about inverse optimization, we need to talk about forward optimization. And forward optimization is nothing more than just an optimization that we already know of, right? Given, let's say, LP, given a C vector, you minimize C transpose X subject to some constraints, and there's a solution X star, okay? Whereas inverse optimization, what it does is, well, I'm going to give you some X, then can you find me a C vector that makes it optimal? That's it. Right? So if this is my feasible region in LP, what I can do is, hey, looks like this solution, say X hat, is the decision that is made by this person. So what is the C vector that makes it optimal? Like geometrically, the answer is quite simple. It's gonna be maybe this C vector, right? If I give you this C vector, then you will agree that this will be the C vector that makes it optimal. But it can actually be any C vector that is, oops, in between this and this, right? Do you agree? And it is more generally a C vector that is within conic combination of these two red vectors, right? If you pick any C vector that is inside the conic combination of these two, right? It's going to be the C vector that can make that solution optimal. Okay? So very simply put, this is how inverse optimization works in an LP setting. Any questions? Yeah. Is the constraint vector A Oh yeah, you can assume that A and B are all known and it is only the C vector that is unknown. But there are also versions of inverse optimization where some of the A's and B's are also unknown. Then can you try to find all these parameters that can really fit the given data? Or given data, what I mean is like given decisions. Now, but the problem is that if you have like too many parameters unknown and only few decisions from which infer these parameters, what happens is the problem becomes like underdetermined problem, right? There are going to be infinitely many set of like numbers or parameters that can actually equally make the decisions optimal. So, but you have to be a bit cautious. Okay. Any other questions? Now I have a question. How would you formulate an inverse optimal problem? How would you formulate a problem that actually finds that C? Like visually, like geometrically, if you look at this geometry, the solution is easy, right? It's going to be a C vector there. How would you formulate this problem? Given X hat, find me a C vector that makes it optimal. In other words, it is equivalent to saying, find me a C vector that allows the given solution X hat to satisfy LP optimality conditions. It's the same problem. And what are the LP optimality conditions? Dual feasibility and complementary slackness slash what? Strong duality. So all I'm saying is that this problem is equivalent to finding a C vector such that the given solution X hat satisfies both dual feasibility and strong duality, or equivalently, complementary slackness. Okay, so we can use LP optimality conditions to derive its inverse problem, right, given that LP. So, well, the LP, you minimize C transpose X subject to AX greater than or equal to B. So the dual, if we define Y to be the dual variable of that single constraint, then the dual constraints look like this, right? And here my assumption is that we all know how to dualize an LP. Okay, this dual feasibility constraints and strong duality, or let's start with the complementary slackness first. This is complementary slackness, and this is strong duality. In either way, it's the same. So these are the LP optimality conditions. So what that means is the problem becomes finding a set of C vectors and also Y such that A transpose Y is C, Y is non-negative, and you can choose either of these two conditions, right? Be it complementary slackness or strong duality. That is all I need. Like this, the simplest version that you can think of when it comes to an inverse optimization problem. Does that make sense? Okay. And now this is a feasibility problem in that you want to just find all C's that satisfy this, but sometimes you want to have some kind of objective function. Maybe you can do this, where C hat is some initial belief, right? I feel like C should be this. So you're giving some initial belief, and I'd like you to find a C that satisfies all this while, right, being as close to possible, as close to that given initial belief C had as possible. Okay? Or what you can do is you can regularize your C in the sense that C has to belong to some set big C. And why? Because if you look at this problem of finding C's, there could be infinitely many such C's. And one caveat of looking at this problem, like using this problem, is that C equal to 0 can actually be feasible. And it makes sense because C equal to 0 means you don't have anything to optimize, and therefore any solution can actually be optimal. So I don't want that to happen. So maybe, right, you can define a C set that is in the sense that, well, big C is set of C is such that a P norm of C is 1. So you're basically normalizing your C. Okay? Any questions? Right? So idea, well, find a C vector that allows the given solution to satisfy optimality conditions. In LP, it's the dual feasibility and complementariateness. That's it. Now, what if this problem, the forward problem, is convex? Not LP, nonlinear, but convex. And the problem becomes what? Finding a C vector that allows the given solution to satisfy what? The more general KKT conditions. That's it. Okay? Okay, so IEIO, that's how it works. Now, in an LP setting, right, where it is only the objective function coefficients, you're trying to find a C vector that fits data. It's almost kind of model fitting. And in some sense, you can think of IO, inverse optimization, as regression. You're fitting a model versus data so that the objective function can explain the data as much as possible. So IO is really some kind of machine learning problem where, more specifically, it is a constrained regression problem in the sense that it is a regression. It tries to find an affine function, right? But then there's constraints. What are the constraints? The constraints are the LP optimality conditions. Okay? So there's some relationship between IO and ML in that regard. Okay, so are you actually happy with this visualization? I give you C hat and you find a C. I'm sorry, I give you an X hat and you find a C. The critical assumption that I'm making here is that X hat is actually on the boundary of this polyhedron, which means the decision maker was actually mathematically optimal in his or her decision making, which is kind of, you cannot really expect that in real life, right? So what I like to consider is the setting where the given solution X hat is not even a candidate to be optimal, meaning it is strictly inside of the feasible region. What happens? Like this. My X hat is in the strict interior of the feasible region. And then the goal is now to find a C vector that makes that given solution as optimal as possible. I know I cannot make it exactly optimal, but maybe there's a way to make it as optimal as possible by minimizing the optimality error associated with the solution. Does that make sense? So what I can do is instead of trying to make X hat exactly optimal, I can allow some deviation, like some perturbation like this. Okay? I'm going to make that perturbed solution optimal instead. How? Well, by making sure that the perturbed solution satisfies primal feasibility and also the dual feasibility, which is this. And then let's say strong duality. Right? So the structure is exactly the same, but instead of X hat, I'm just plugging that X hat minus epsilon into these problems. That's the only change. Now, I am making my perturbed decision optimal, but again, like to minimize the optimality error associated with it. So what that means is while I do this, I want to minimize my epsilon by minimizing some norm of epsilon, be it like one norm or any p norm in general. Okay, and of course, C is supposed to be in some normalization or regularization set, big C. That's it. Now, if I solve this problem, what would be the C vector that my inverse problem will give me that makes that solution as optimal as possible? It is probably this guy that is perpendicular to that hyperplane, that face of the polyhedron. Why? Because if you look at this, it is this vector. When you actually solve the forward problem with this vector, then there's this distance between the given solution and what can actually be optimal with respect to this C vector. That is the smallest distance that it can achieve. Okay? If you gave me this C vector, then your optimal solution is going to be here, and therefore there's going to be this much of difference, and et cetera, et cetera. Okay? Any questions? Okay. I'm going to move on, right? Using this framework, we can further generalize by considering multiple decisions. What if there's not only a single decision given, but multiple decisions like, x at 1, x at 2 through x at k? Then I'm looking at this kind of geometry where I have bunch of decisions like here. Then can you find me a C vector that makes all of them as optimal as possible? Well, you can do exactly the same, but all you need to do is just to introduce different perturbation vectors for different data points. And then in the objective function, we minimize the sum of the perturbations. That's it. And by the way, this one way to define a loss function, but there can actually be different loss functions that you can think about. I'm going to show you later. Okay. And I'll find a C vector, and it could be like this, where there's going to be a bunch of distance between that face or hyperplane with each of these data points, or it could be this, and it's going to be the vertex from which you assess all the distances from different data points, something like this. Does that make sense? Okay. So that's the most basic version of inverse LP. Of course, too easy to be true. Okay, and of course, there are variants of inverse LP, right? So one variance is to incorporate the robustness and stability consideration into this format, right? And the reason is because if you think about how regression works, linear regression, right? Bunch of data, right? And you fit a line. Now, if some of the data shift, like move to the right or to like upward like this, what happens is chances that your model can actually be very different from the initial model, right? Or even you introduce some 3 outliers like this, then your model can actually change drastically. And now similar phenomena can actually happen in inverse optimization. So how do we improve the basic inverse optimization model to address this kind of instability issues is one of the increasingly popular topics in the group. Okay, so I'd like you to think about this, right? So there's the feasible region that only consists of like 4 constraints, and there are 4 data points. And you solve the classical inverse LP, then what would be the C vector that makes the 4 data points as optimal as possible? It's gonna be maybe this C vector, right? Because it is that line that is closest to these 4 data points compared to the other 3 lines or 3 hyperplanes in general. Okay, that's it. So let me call the constraint vectors of these 4 constraints A1, A2, A3, and A4. So they look like this. Then if you solve the naive traditional inverse LP, then it'll say, well, I put the arrows in the reverse direction. But the inverse solution for the inverse problem is going to be that C star, the inverse C vector is going to be exactly A1. You agree? Yes, right? And now let me move these two data points little by little and see what happens. I'm going to move them to the that direction, little by little. Then all of a sudden, you can imagine that the solution to the inverse problem will drastically change, immediately change to or jumps to A2, right? There's no transition. It'll change its solution from A1 to A2 all of a sudden, okay? And if you think about like fitting a model, this kind of inference is not desirable. The change is too big, too drastic, right? Too all of a sudden, okay? Now, another phenomena is something like this. Go back to the 4 data point setup, and let's say there's that outlier highlighted in that red color. What happens if you feed these 5 data points into inverse optimization? Again, it'll all of a sudden say, before it was A1, but now that I see that outlier, I think it should be A2. Just a single outlier, but it says preference is very different, like before and after. Okay, not good. Okay, so small shift in the data and small number of outliers can actually have huge impact on the way inverse optimization works. And we call it, well, being basically inverse unstable. The way inverse optimization works is unstable in response to such data imperfection or data noise or uncertainty. Another imperfection that you can think of is the following. Let's say, given these 4 or 5 data points, inverse problem says, I'm sorry, this has to be the C vector. Now what happens is, well, if you think about the goal of inverse optimization, you're going to use this C vector for solving the forward problem. If you're lucky, if you solve the forward problem, your X star can actually be here. But if you're unlucky, if you solve the forward problem with this C vector, then chances that you might actually end up with that solution that is actually very far from the majority of the data points. It actually serves that outlier and misses the majority of the data points. Not good, right? That defeats the purpose of inverse optimization, okay? And call it, it is forward unstable in the sense that it is unstable, right? In a way, how C vector performs when it's plugged into the forward problem, forward unstable. Now, if you think about it, this can actually happen in real life quite frequently because we change our decisions like daily, maybe because our preference changes. But really, like the inverse problem, to catch that change gradually and smoothly and slowly, not drastically, like how we showed that in that example. Okay, and also it could be that what you saw in the data might actually not be true because of some measurement errors, right? Some noise. And almost always there's going to be some outliers in decision data. Okay, so it's critical to capture and address this kind of instability issues in inverse optimization. And if you think about it, that's what people do in machine learning. For example, robust regression. Right? There's regression, they saw some problems, issues, so they developed robust regression. Well, similarly, can you do this for inverse optimization as well, right? And then if I think about it, well, there's no such thing as stability that is well defined in the inverse optimization literature, but then some papers have suggested stability measures, and one of them is the following. It is called the inverse stability measure. And what is it? It is the minimum tolerable data shift until your initial C vectors are all lost. Given initial data, your inverse optimization model says this has to be your C vector. You perturb your data, and at some point, it'll lose all the solutions that it suggested at first. Okay? And you measure the minimum tolerable data shift, and that's going to be the measure for inverse stability. And mathematically, we can express it like this. X hat is the given data set. X is the data that is being that has been perturbed. Okay. And C of X hat is the C vectors that your inverse model gives based on the initial data. C of X is the set of C vectors that the inverse model gives based on the shifted data. When their intersection becomes an empty set, give me that distance, and more specifically, the minimum distance. That's how you measure instability for inverse optimization. And if you think about it, that's exactly how what is called the breakdown point works in regression. Have you heard about the breakdown point in regression literature? What is it? It is the point at which you started with some regression model, you add outliers or shift some data, and at some point, your model will become completely different, right? And what is the proportion of data that you shift or the number of outliers that you add to the model that happens, right? In like ordinary least squares, like OLS, breakdown point is 0. Whenever you try to change something, your model is going to change, right? If you think about the least median of version of regression, then the breakdown point is going to be 50%, right? Half of the data points are moved, then you're screwed, something like this. So, so basically, this measure is adopting this interesting idea of breakdown point, translating that into the inverse optimization context. For the instability, what happens if I actually use C? Will I actually achieve an X star that is actually close to the initial data? Well, we define the forward instability as the worst case distance between the given data and the argument set of the forward problem if you actually use a certain C vector. Okay? So minimize the worst case distance as much as possible. Okay. So what's the idea? As I mentioned, the inverse stability is inspired by the breakdown point used in regression. And also more generally, if you think about how regression people address this kind of instability, they propose robust regression methods. And one of them is to really minimize the data quantile statistic instead of minimizing the sum or average least squared errors, right? So data statistic or data quantile statistic, what that means is, well, when I try to fit a model, I'm going to only consider, let's say if data is 80%, 80% of the data point. Okay, I'm going to do my best to serve whatever those 80% of the data points that help me, right? And the rest of it, like 20%, I'm going to like treat them as outliers. Something like this, right? It is called least twin squares or least quantile of squares. So we can adopt that spirit here to really find a C vector that minimizes the data quantile optimality error instead of minimizing the sum of the optimality error for all data points, right? So it's quantile based. So as how it is named in regression, there's this name quantile inverse optimization. It's a variant of inverse optimization for stability purpose. Okay, so all you need to do is exactly the same format, right? The constraints are the same: dual feasibility, primal feasibility, and strong duality, the normalization. All we are adding here is that red constraint that ensures that it is always that specific data point that corresponds to the 80th, right, best optimal error achieved by the C vector that is contained by or that is bounded above by a certain threshold. Okay? You just find me a C vector so that if you use that C vector, 80% of the data points, right, their optimality errors is going to be no greater than some threshold tau. And 20% of data points, they might actually have worse optimality errors, but I don't care. That's it. Right? So here, epsilon superscript k of theta is really, that index k of theta is the data index associated with the theta times k smallest optimality error, where k is the number of data points. Let's say there are 100 data points, and theta is the proportion that I want to care about, let's say 80%. Okay? So find me a C vector such that 80th smallest optimality error is still less than or equal to tau. Okay? So this is analogous to quantile-based regression, basically. Okay? Any questions? Right. So this problem is a quantile inverse optimization problem. Okay. And there's some interesting structure of that problem that will lead to a very nice reformulation. And the reason why we need reformulation is because, well, this problem looks simple, right? Looks simple, but what is happening here in that red constraint is a bit messy. Good question. Because, well, you could actually introduce some objective function, but for now, I'd like to just find any C, right? Can you give me a set of C vectors that'll make this happen? That'll make 80% of data points happy. Yeah, I removed the objective function intentionally to really focus on the structure of the constraints, right? And then later on, I'm going to introduce some objective function. Yeah, okay. Yeah, this problem, a feasibility problem, no objective function, just find me any C vector that satisfies this. Now, written in a compact format, but if you look at that, oops, if you look at this guy here, I'm saying 80th smallest optimality error. So what that means is there's some combinatorial nature here. I'm supposed to be counting each of these 100 data points to check, hey, are you within tau? Are you within tau? I'm supposed to be doing this. So inside that, if you were to write that constraint extensively, then you will have to introduce like binary variables. This becomes essentially a combinatorial optimization problem. And I don't want to solve it as a combinatorial optimization problem because, well, notoriously hard. But, well, is there any better version of this? That's the goal. Now, there's some theory that I wanted to show. Well, that basically says the following. I'm going to use animation, right? What that statement is saying is that, well, if that QIO solution is feasible, if there exists a C vector that satisfies those constraints that you saw, right? There exists a solution that is actually one of the AI vectors, which is perpendicular to one of the hyperplanes of that constraint or faces of the constraint. Does that make sense? And that happens when there is this data point that is within tau distance with this hyperplane, right? If yes, then this A2 vector is going to be one of the feasible C vectors for that feasibility problem, this problem, okay? And also, if you look at this, right, A1, the hyperplane or the constraint that corresponds to A1, that guy is also the distance between the data point and this is also within tau distance. So A1 can also be a feasible C vector. Do you agree? A1 and A2 can both be feasible solutions for a C vector. And again, there's no objective function. I'm trying to find any C vectors. A1 and A2, they work. Okay, first theory. Both A1 and A2 are inverse feasible. Now, the second theory is the following. It's also written in math, but really the intuition is the following. Now, A1 and A2, they are both feasible C vectors for the QIO problem. Now, find the intersection of the two constraints, right, that correspond to A1 and A2. And the intersection is going to be exactly this. Right? I'm going to use blue color. Okay? And the intersection of these two facets, I want to measure the distance between that intersection with the initial data point and check whether that distance is also within tau. Okay? And if the answer is yes, what happens? Well, it turns out that if you pick A1 and A2 and find any conic combination of A1 and A2, right? In this case, it's going to be anything here, right? Can actually also be a feasible C vector for this QIO problem. Does that make sense? So this problem, geometrically speaking, is all about matching data points with the facets or the hyperplanes of the polyhedron. I'm trying to find the facets that are within tau distance from data points, collect them, right? And find the intersections of different hyperplanes to find this corner point, for example. And if the distance between the corner point and the data point is tau, then that declares, well, that basically says that you can just do any conic combination of these chosen two AI vectors. In higher dimension also works. Okay, so the problem is really to find AI vectors such that the intersection of hyperplanes is within tau distance from at least data times k data points. Right? In this case, I only show you one single data point, but we'll have to think about data times k data points, like 80 data points out of 100. So it's all about counting. So we can reformulate that problem into, well, this problem. Okay, I'm just drawing that formulation, but really try to show you how it works. Well, there's this epsilon, which is the optimality error. There are two binary variables, v and u. Let's see what the roles of v and u here. V, binary variable. If v is 1, what happens? If v is 1, this becomes, well, 0, then you're basically tightening this constraint. And what that means is you'd like the perturbed solution to be exactly on that hyperplane that corresponds to AI. Okay? That's the interpretation. What about the u guy? The u variable is also binary variable. If u is 1, what that means is this becomes 0. So you are actually trying to make that k data point non-outlier by making it satisfy its optimality condition to be no greater than tau. If u is 0, well, you don't care about the optimality error for that data point, and I want to make sure that the number of u's that are assigned 1 is greater than data times k. It's cardinality constraint. That's it. Okay? And by solving this problem, you can find a bunch of different C's. Okay? And at the end of the day, your the set of feasible C vectors for this problem is nothing more than really a conic combination of AI vectors whose corresponding VI star variables are assigned 1. VI is, well, are you going to choose that vector or not? Okay? So that's the first reformulation. Then if I think about it, right? Well, there's something else, right? So here, this is, again, a feasibility problem because you don't have any objective function. Now, we can also introduce the objective function of maximizing the sum of v's. What that means is maximizing the number of AIs that are chosen. And by doing so, you can actually further increase the stability of your solution. Why? Because if you think about it, you're trying to include as many hyperplanes as possible, as many AI vectors as possible. Right? You're being more robust and robust because if you have more AIs in your bucket, right, you have more time to lose in a way as your data is being perturbed. Right? You lose this, you lose that, but you have like more than other solutions in terms of what you can lose. Okay, so there's this theory on that, but I'm going to move on to the next part of this work where we actually view this problem as a maximum edge by-click problem. What that means is, as I told you, it is always just matching some data points with some of the hyperplanes or the corresponding vectors. So what that means is you can express this problem in this kind of bipartite graph setting. Okay? That means is the goal becomes trying to find a subset of AIs, right? Subset of the constraint vectors, right? With max cardinality that can cover some data points. And what are some data points? I want to cover at least data times k data points, right? And that is actually called the maximum edge by-click problem. It's a well-known problem. So what that means is once this problem we thought is complex combinatorial problem, well, is becoming a problem that is already well known in the literature. So what we can do is adapt some well-known algorithms for bipartite graph related problems to solve similar problems, either exactly or approximately. That's the takeaway. Okay. Mhm. And hierarchy, you mean? Right. There are going to be a lot of ties. There are going to be a lot of ties, right? Different combinations, different cones that might actually compete against each other. And that's one of the reasons why I like to find a conic combination that includes as many AIs as possible. And when there are ties, well, I don't know if there's any specific tiebreaker, right? Right. But you can also simulate it, right, by actually propagating like the actual noise in the decision data to assess the performance of different conic combinations that you believe are basically tied with each other. Okay. Okay. Convex, well, that's basically how we do, right? So I told you I'm going to be talking about algorithms, and this is type of the algorithms that I like to talk about, right? So you identify a problem, you formulate this model, the model feels just too crazy. Is there any structure that you can take advantage of? And there's that geometry that eventually leads to the well-known problem, and there we go. Okay? It's a nice way of thinking about your modeling. So that's for inverse LP. Inverse convex programming, where F and G, all of them are convex. The inverse problem is the same, but I like to be a bit more general in the sense that now, in addition to objective function coefficients, why don't we actually try to cover any parameters, including those in the constraints, right? So this time it's going to be the theta that you'd like to infer. Can you find theta that makes a given observed solution or decision X hat as optimal as possible? That's the goal for inverse convex programming. Now, if you think about it again, well, it is equivalent to finding a C vector or the theta parameters that allow the given solution to satisfy KKT conditions. This guy is the stationary condition. This guy is the what? Complementary stuckness, right? It's the KKT conditions. Optimality conditions for convex program is the necessary and sufficient conditions, actually. Now, that's when that's the case for a single data point. That data point is actually on the boundary of the feasible region. What if the solution is actually off of the boundary inside of the feasible region? Well, you do exactly the same. Instead of trying to find X hat satisfying KKT conditions, you perturb them by epsilon and you minimize the sum of the epsilons. Exactly the same analogy, but with KKT conditions. Now, there are different versions of loss function, as I mentioned. Instead of minimizing the epsilon, right, in the X space, you can also try to minimize your loss in F space. Try to minimize the regret in terms of objective function value. Okay? So if X hat is the given solution and you find theta and you can evaluate the objective function value like this. Now, given that data that you just found, you can actually find an optimal solution for that data. Okay? And there's going to be some regret in between. So that's going to be the loss that I want to minimize. So another way of thinking about how we formulate a loss function. That's it. Now, there are also different types of generalization in inverse optimization. Now, one way to think about it is, hey, so we talked about this stability when X hat is uncertain, but can we actually apply distributionally robust optimization to inverse optimization, for example? So what that means is, hey, X hat, I think it follows some distribution. So I made my efforts collecting all this data and established some kind of empirical distribution. But I'm not too confident about that empirical distribution. So what I'm going to do is I'm going to define an ambiguity set around that empirical distribution. Now, my goal is to find the theta or C vector that makes my data points as optimal as possible, but not only those data points that are being observed, but also all those that could actually be sampled from a family of different distributions, right? So DRO, take on IO, has also received a lot of attention recently. So before I start, let me see if there's anything important that I wanted to say that I missed. And yeah, I don't think so. Okay, so yeah. So when it comes to this, well, you can also introduce different loss functions. And there are different loss functions like identifiability loss, predictability loss, and suboptimality loss. We basically talked about all of them already, right? Predictability loss is the loss function defined in terms of X space. Suboptimality loss is the loss function defined in the F space. Identifiable or identifiability loss is the loss against the true parameters. But in real life, we never know what the true parameters are. So identifiability loss is only relevant for kind of validation purposes, right? Not in real life. Okay, so I'm going to stop here, right? And we're going to resume at in 15 minutes. Is that right? Okay. Okay, thanks. Okay. Okay, now we are, I think, pushed back by around like 10 minutes. Um, but I feel I can finish in time, lecture 4. So the last topic that I wanted to really cover are the two different variants of I/O, more advanced versions of I/O. One is called conformal I/O, and the other is called contextual I/O. Conformal I/O, you might have actually heard like conformal prediction, right? When you predict, right, you want to make sure you want to have some guarantee about like out of sample performance. Okay. Now, if you think about I/O, let's say in I/O, of course, I mean inverse optimization, right? When you think about I/O, let's say you solve some version of I/O and you obtain this parameter, theta bar. Okay? And if you think about the purpose of inverse optimization, you'll be now using this theta bar for your forward convex program to generate new decisions for the decision makers from which you collected the data, right? Either to be able to predict his or her behavior or to generate decisions for him or her, right? But then, well, if the decision data were uncertain and noisy and following some kind of distribution, how do we know how well this estimate will actually perform out of sample? Right? That's a real question. Okay, this actual out of sample performance is what really matters if you think about the goal of I/O. So I mentioned that one way of addressing uncertainty is to introduce like DRO component in I/O. That's one way of doing it. What I found really interesting that is recently studied is what is called conformal I/O. What it does is basically instead of trying to use that exact estimate data bar for future decision making, I'm gonna put some margin around it, right? Some margin around it, and then I'm gonna be using them in my decision making. So, right, you can think of it as some kind of uncertainty set around theta bar. Then what that means is in the forward problem, you're gonna be solving a robust convex program. Okay? So what I mentioned before the break, right? The DRO version incorporated in inverse optimization, right? That uncertainty set is inside inverse optimization. Whereas this version, you obtain theta bar using IO. And when it comes to actually using that theta bar for solving the forward problem, you can put some uncertainty set around it, and you can use that uncertainty set and treat your forward problem as a robust optimization problem. A bit different perspectives. Okay? And now, Again, in robust optimization, always a question is how to set up the uncertainty set. And one way that is suggested is this, right? So once you have theta bar from your inverse optimization, you define an uncertainty set that is big C of theta parameterized by this alpha. And that alpha is basically the size of cone that kind of includes the original estimate theta. Okay, that is written here. Okay, roughly speaking, you're kind of, this is theta, and you put some margin around it. You're going to treat this as your uncertainty set, which will be used for solving robust forward problem. And of course, you have this normalization constraint. You might have noticed that I sometimes use one norm, this one uses two norm, and I might have actually used p norm in general. Well, it's just user-specific choice. It's just user-specific normalization. But anyways, okay. Now then we think about how to actually find the uncertainty set. What really matters is what should be alpha. Because alpha is too big, then my uncertainty set is too big, and my solution is going to be too conservative. And that might actually, well, too conservative with not much of addition in solution quality, something like this, right? So I want to be sensibly conservative in a way that I minimize the size of the uncertainty as much as possible by minimizing alpha. Okay, I want to minimize alpha, and I want to minimize alpha while I make sure that when I actually use some data that is sampled from that uncertainty set, okay, that theta k parameter is going to be actually in that set, right? Well, if you solve an inverse optimization problem, right, for new validation set, which you have never seen, okay, you solve it, and you're going to make sure that theta k is actually inside of the uncertainty set that is based off of the initially obtained theta parameter. Okay, so the difference is that theta is determined based off of your training set. And you want to validate the performance of your training set based estimate theta bar by guaranteeing that if you solve the inverse problem for new data, validation data, unseen data, then the new theta k is going to be still inside that uncertainty set. And you're counting how many of your validation set data points satisfy this. You want to make sure that, well, this version, like gamma percentage or gamma portion of your validation set data will satisfy this, right? That theta k is going to be inside that uncertainty set. Okay, this is how you guarantee your out-of-sample performance by explicitly writing the probability that for a given validation set that your uncertainty set will actually include the newly observed or estimated theta, right? For no less than gamma percentage of the size of your validation set, right? So k-val is the set of data points and the validation set, of course. Okay? And of course, this guy is a user-specific parameter. So if you think about it, this is very similar to the quantile inverse idea where you're actually counting data points and making sure that at least like 80% or 90% of data points will be working, roughly speaking, fine with the estimates or the uncertainty set around that estimate. Okay? So that's basically how conformal I/O works. So the big picture idea is that, well, once you get a C vector or theta vector, put an uncertainty set around it, and you're going to treat the forward problem as a robust optimization problem. Okay? And always when it comes to robust optimization, how to characterize, how to define an uncertainty set is often the most important task in modeling. Okay? And the next one is contextual I/O. And more specifically, we can see I/O as some kind of supervised learning, for example, where there's this exogenous signal or context parameter, UK, and per each exogenous signal, there's an observed decision. Okay? So what is that exogenous signal or context parameter? For example, you can think of it as different graphs. Think of the shortest path problem. If you give a certain driver like graph A consisting of a certain set of nodes and arcs, and graph B consisting of like different sets of nodes and arcs, right? Their behaviors or his or her behavior, of course, will really depend on that specific context, right? And the specification or the characteristics of the graph is, well, can be seen as U, right? U1, U2, U3. And for each U1, U2, and U3, there's going to be X hat 1, X hat 2, X hat 3, the observed behaviors. Now, still, you'd like to find theta or C vectors that makes the given solution optimal. But more specifically, in this case, I like to make them optimal for like each of these contexts. Okay? So slightly different from the traditional inverse optimization in the sense that I didn't think about any contextual information in the very first version of inverse optimization, right? Now, if you think about it, why that matters is because, well, if I just give you different graphs, right, different nodes and arcs and different routes, then you might actually be tempted to just train your machine learning model directly from U to X. Okay? Whereas what inverse optimization can do is it can take a detour. I'm going to take U, but instead of just predicting X immediately, like directly from U, I'm going to take a detour by actually inferring this behavior's preferences. Okay? I'm going to use those preferences to predict his decisions for different contexts. You see the difference? Right? So what I said earlier is you can think of it as some kind of imitation learning. Imitation learning. I give you a starting point and the destination point. Like, can you predict the route? Right? You observe the driver's route choice and try to immediately, like, directly learn his behavior versus, hey, why don't I actually learn what he was thinking? And there are many features that he cares about. It's gonna be like how crowded a certain route is, or is there any gas station? Is there any school district that you want to avoid? Something that has not been captured in route decisions or the observed routes. Okay. Can you learn the preferences and then use that as a mapping or indirect relationship between U and X hats? That's the basically takeaway of this supervised learning like contextual I/O. And the reason why this is important because, well, if you try to just blindly and naively learn how he drives, right? Oftentimes there's no clue. But if you understand his intention, preferences expressed in the objective function, you can actually carry that objective function to any settings. Be like if you see a network that like no one has really seen before, what matters is you still like know his intention, preferences. All you need to do is just solve a new shortest path problem with that learned objective function, and there's gonna be accept. Okay, that's it. So that's I/O. So takeaway, I/O is a machine learning problem, but with optimality conditions to understand the decision maker's behavior. The critical assumption here is that decision makers are supposed to be rational decision makers or reasonably rational decision makers. Garbage in, garbage out applies to I/O because, well, if someone gives you some nonsense decisions, try to learn preferences, no way, right? So you have to, as a modeler, be very cautious in identifying what data that you want to use, and you can ask your client, hey, can you label this decision, right? What do you want me to learn your preference from? And probably not, right? So good decisions, bad decisions, can you label them? Could be an interesting take on like practical use of inverse optimization. Okay, so there are some references. that cover some seminal papers in inverse optimization. That also includes IRL papers at the end. Okay, so with that, I'm going to move on to lecture 4.